Hey everyone, and welcome to today's Explainer. Today, we are diving right into the absolute core of Algebra I, which is all about relationships between quantities. Now, we aren't just going to be memorizing formulas here. We're actually decoding how numbers interact in the real world. I want you to think of algebra not as some rigid, boring set of rules, but as a brilliant structural blueprint for understanding and balancing quantities. So let's jump right in and build that rock-solid foundation.
So here is our main learning target for today. Our goal is simple but incredibly powerful. We are going to translate a relationship between quantities into an equation or an inequality, solve it while preserving equivalence, and then check that the result actually makes sense in context. And you know, that phrase right there, preserving equivalence, that is literally the secret to all of algebra. It's fundamentally about balance. Whenever we manipulate an equation, we're just strategically applying properties of equality to keep the scales perfectly aligned.
To pull this off, we need a reliable system. So we've got a 5-step blueprint that you can apply to model pretty much any algebraic relationship. Step 1. Name your quantities and your units of measurement. Step 2. Define the variable for your unknown number. Step 3. Actually write the equation or inequality. Then step 4, this is where the heavy lifting happens, use inverse or opposite operations to isolate the variable, all while strictly preserving equality on both sides. And finally, step 5, substitute your answer back in to verify it makes sense. This right here is your ultimate algebraic survival guide.
Let's look at how this builds by checking out a proportional relationship in 3 totally different ways. In everyday words, you might say, distance is 65 miles per hour times the number of hours. Now, if we track that data in a table, 1 hour yields 65 miles, and 2 hours yields 130 miles. Distill all of that down into a symbolic equation, and we get d equals 65t. Viewing the exact same relationship across words, tables, and symbols really proves that equations are just direct reflections of measurable, real-world patterns. It's all the same thing, just dressed up differently.
Oh, right. Let's actually put our blueprint into practice. We've got a created practice example here. Solve the equation 3x plus 5 equals 20. In this case, x is our defined variable. It's the unknown number we're hunting for. Our mission is to figure out exactly what value of x makes this statement true. To do that, we're going to skip right to step 4 of our blueprint. We need to apply inverse operations to isolate our variable, and we have to keep those two sides perfectly equivalent while we do it.
So let's execute that first inverse operation. We're going to subtract 5 from both sides of the equal sign. Why 5? Well, we want to completely undo that plus 5 that's attached to our 3x. According to the subtraction property of equality, whatever you subtract from the left side, you absolutely must subtract from the right side. That is how we ensure the equation remains perfectly balanced.
Boom! And here's the result of applying that subtraction property of equality. Our positive 5 and negative 5 completely cancel each other out to 0 on the left, and on the right, 20 minus 5 gives us 15. So we're now left with a simplified, perfectly equivalent equation, 3x equals 15. We're definitely one step closer to isolating x, but we aren't quite there yet, right? Because that x is still being multiplied by 3. To undo that remaining multiplication, we just use another inverse operation, the division property of equality. We simply divide both the left side and the right side by 3. And because we perform the exact same operation to both sides, we preserve our equivalence. The 3 divided by 3 on the left simplifies down to 1, which finally leaves our variable completely by itself. Which brings us to our final solution, x equals 5. Through a rigorous step-by-step application of equivalence-preserving operations, we successfully isolated the variable and found the exact value that satisfies our original condition. But, hold on a second, we cannot stop here. We have a 5-step blueprint for a reason. Let's finish the job by demonstrating that crucial 5th step, substitution. To verify our work, we take our answer, x equals 5, and we substitute it right back into the original equation where the x used to be. So 3 times 5 gives us 15. We add 5 to that 15 and we get 20. 20 equals 20. The equation balances perfectly. This proves, without a doubt, that our solution makes complete mathematical and logical sense in the context of the problem. Now, let's expand our toolkit a bit by comparing equations against inequalities. As we just saw, linear equations generally have very specific solutions, like x uniquely equaling 5. But inequalities, they represent a broader constraint, something like x is greater than 5, because literally any number larger than 5 makes that statement true, like 6, 10, or even 1,000,000. We can't just write down one single number. Instead, we have to describe an entire solution set, which we visually represent as a shaded region stretching across a number line.
All right, it's time for our first knowledge check to see how well we can apply this modeling process to a geometric relationship. Here's the scenario. The perimeter of a rectangle is 54 centimeters, and its length is 6 centimeters. Thinking back to our blueprint, ask yourself, which equation represents this relationship? What exactly does your variable mean here? And what units will belong to your final answer? Let's walk through the deep reasoning for this one together. The correct equation is 2 times 6 plus 2w equals 54. Why? Because a rectangle has 2 equal lengths and 2 equal widths. So we multiply our known length of 6 by 2 and add it to 2 times our variable w. That variable w explicitly represents the unknown width of the rectangle. And finally, because the total perimeter was given to us in centimeters, the units for our final width absolutely must also be in centimeters. Honestly, naming your quantities and assigning the proper units is what gives algebra its real-world power. Moving right along to our second knowledge check. Let's test the deeper structural mechanics of what we're actually doing here. First question, how does substitution actually verify an equation's solution? And second, why is an inequality's answer visualized as a region on a number line rather than just pointing out a single solitary number? So here is the core reasoning. Substitution works so well because it physically proves that plugging a specific value back into your algebraic model makes the statement mathematically true and balanced. Inequalities, on the other hand, are fundamentally different because they represent boundaries or constraints. Because a constraint like x is greater than 5 contains infinitely many true values, it is mathematically necessary to use a number line region to accurately capture and visualize that entire infinite solution set. You just can't list them all out. We have officially hit our learning target today by translating quantitative relationships into algebraic models using equivalence-preserving operations and verifying those solutions in context. Our 5-step blueprint gives you a foolproof, highly repeatable method to navigate absolutely any equation or inequality you come across. By always applying inverse operations to both sides, you guarantee mathematical balance every single time. So I'll leave you with this to think about. If you are paid $50 per week plus $3 per sale, and you want your pay to be at least $100, how would you model this new real-world relationship?